Okay, this is tutorial 9 on buoyancy, and I'm just going to go through the tutorial for those who are still struggling. I'm going to share my screen here. And okay, we have a beaker of water, and we have this cube, this block that we push down to the center of the cube, center of the beaker rather. And we know that this is a cube that floats in water. And so we let go of it and we ask what the motion will be, and it will accelerate up to the top of the beaker and float. And then we're asked to draw a free body diagram for the block at the instant that it's released. And so we know that our diagram had better scream that acceleration up. Now, we're supposed to show the forces that the water exerts on each of the surfaces of the block separately. So if this is the water to the right, then it's going to push with a force, let's call that a normal force by the water on the right. And if this is the water on the left, it's going to push with a normal force by the water on the left. Now, I know that when I'm in a fluid, the pressure gets bigger as I go deeper in that fluid. And so that means that the push down by the water on top has to be less than the push up by the water on the bottom. And then there's one more force, that is the weight force, earth pulling on the block. Now, I know that the vertical forces, I know that the normal by the water on the bottom pushing up has to be greater than the normal by the water on the top pushing down. And it's got to be bigger than both of the downward forces, which would include the weight of the block. If you cannot completely rank all the forces, explain why not. We don't know the mass. So I don't know which of these two forces is bigger, the force by the water on the top pushing down or the earth pulling down. I don't know which one's bigger because I wasn't told anything about the mass of the block. Did I use the relationship between pressure and depth to compare the magnitudes of any vertical forces? Well, yes. I knew that the normal by the water on the bottom had to be greater than the normal by the water on the top. Did you use any information about the motion of the blocks to compare the magnitudes of any of the vertical forces? Yes. We knew that the acceleration was up, and therefore the net force was up, and that's how I got this relationship there. In the box at right, draw an arrow to represent the vector sum of the forces exerted on the block by the surrounding water. Well, I know that the force to the right by this water on the left is going to cancel this force to the left by the water on the right. That's just symmetry. And so I know that the push up by the water on the bottom of the block is going to be bigger than the push down by the water on the top, again, because the pressure gets larger as you go deeper. And so the sum of all the forces on the block by the water would be this upward force that we call the buoyant force. Is this vector sum the net force on the block? No. We did not include the weight force. Is the magnitude of the sum of the forces exerted on the block by the water greater than, less than, or equal to the weight? It would be greater than. And again, that's because the acceleration is up. Now we repeat this experiment with a second block that has the same volume and shape as the original block, but this one is observed to sink in the water. So if we draw a free body diagram for this block, we know that, again, we have the horizontal forces. This is by the water on the left, pushing to the right. This is the normal by the water on the right, pushing to the left. This is going to be the push by the water on the bottom, pushing up. This will be the normal by the water on the top, pushing down. And then we have this weight force that now is big enough to essentially accelerate this down to the bottom. Which forces are the same in magnitude and which are different? Well, if we're starting at the same location in the beaker, in the middle of the beaker, all of these forces by the water will be the same. And the only one is the weight. So the weight force is different. All the others are the same. Do any forces appear on one diagram but not on the other? No. Same forces. In the space provided, draw an arrow to represent the vector sum of the forces exerted on the block by the water. Well, it's the same water in the same location, pushing in the same way. And so this buoyant force is going to be exactly the same as it was on the first page. So it's going to be same. Now, imagine that you were to release the block from part B at a much greater depth, down in the Marianas Trench, for example. State which of each of the following forces on the block would be greater than, less than, or equal to the corresponding force on the block in part B above. Well, the upward force on the bottom surface of the block would be greater because the pressure down there would be greater. The downward force on the top surface of the block would be greater, again, because the pressure down there is greater. But the vector sum of all the forces on the block by the surrounding water doesn't change. So that's going to be exactly the same. And that's because that formula for pressure is linear. It only depends on the height, which would be the P1 would be here. P1 would be at the top of the block and P2 would be at the bottom of the block. And that would give me P2 minus P1 would give me the pressure difference And that only depends on the density. And the density of the water is going to be the same down in the bottom of the Marianas Trench as it is in the beaker. And the gravitational field strength is the same. And the distance between point 1 and point 2 remains the same. The vector sum of the forces exerted on an object by the surrounding liquid is called the buoyant force. This force is customarily represented by a single arrow in the free body diagram. I just read this bottom sentence here. So let's move on to page 3. In general, does a buoyant force on an object that is completely submerged in an incompressible liquid depend on the mass or weight of the object? It did not seem to. We had two different blocks that had the same volume but different mass, and we got the same buoyant force. What about the depth below the surface that the object is located? That doesn't depend on, the buoyant force doesn't depend on that. What about the volume? Well, yes, that very much influences the buoyant force, because that's going to determine the pushes from the bottom and the pushes from the top. Displaced volume. Consider two blocks of the same size and shape, one made of aluminum, the other of brass. Both blocks sink in water. The aluminum block is placed in a graduated cylinder containing water, and the volume increases. The volume reading increases by 3 milliliters, or 3, this is the same as 3 centimeters cubed, the same as 3 cc's. By how much does the volume reading increase when the brass block is placed in the cylinder? It would be 3 centimeters cubed, or 3 milliliters. And that's the experiment we did in lecture, where we put the two bottles down at the bottom of the liquid, and where the bottles were now, liquid used to be. And so it's just the volume of the object, not the mass of the object, that matters when something is completely submerged, when it sinks to the bottom. When an object is placed in a graduated cylinder of liquid, the increase in the volume reading is called the volume of liquid displaced by the object. Does the volume of water displaced by a completely submerged object depend on the mass or weight? No. What about the depth below the surface? No. What about the volume of the object? Yes. What about the shape of the object? No. Okay. According to Archimedes' principle, the magnitude of the buoyant force exerted on an object by a liquid is equal to the weight of the volume of that liquid displaced by the object. Now, not all of those words are required. Let's get rid of some of them. Okay, let's read it again. According to Archimedes' principle, the magnitude of the buoyant force is equal to the weight of that liquid displaced by the object. Okay, that seems less wordy and a little bit easier to comprehend there. So I'm gonna just kind of scratch those out. Consider the following statement made by a student. Archimedes' principle simply means that the weight of the water displaced by an object is equal to the weight of the object itself. That is, that's only true if something floats. We found in the earlier exercises that if I have acceleration up, something accelerates to the top, then the buoyant force would be greater than the weight. And if it accelerates down, then the buoyant force would be less than the weight. Okay, we're zipping right along here. In this last page, we have a rectangular block A, and when we release it from rest at the center of the beaker of water, the block accelerates upward. It accelerates upward. At the instant it is released, when it's in the middle down here, is the buoyant force on the block greater than, less than, or equal to the weight? Well, the buoyant force would be greater than the weight, and that's because it's accelerating upward. So my free body diagram needs to scream up. When the block A reaches the surface, it is observed to float at rest as shown. In this final position, is the buoyant force on the block greater than, less than, or equal to the weight? It would be equal to here, because now the acceleration, so it would be equal because the acceleration is 0. Are your answer to the questions above consistent with Archimedes' principle? Yes, the volume, when it is the volume displaced, when it's completely submerged, is greater than the volume displaced when it floats. And that's because when it floats, it's only this part that is below the surface that is displacing liquid. This part that's sticking up over the top of the surface is not displacing liquid. Now we have a second block of the same size and shape as A, but slightly greater mass. When we release it from rest at the center of the beaker, the final position of this block is shown at right, and you see that it's just barely sticking up above the surface. How does the buoyant force on block B compare to the buoyant force on block A at the instant they are released? Well, that would be the same, because the two blocks, if they're in the center of the beaker, are both displacing their entire volume. So the volume displaced is equal. In their final positions, the buoyant force on A is going to be less than the buoyant force on B. And that's because the volume displaced is less for A. Now we have a third block, C, that is the same size and shape as A and B, but slightly greater mass than block B, and it's released from rest at the center of the beaker. Two students predict the final position of the block and draw the sketch at right. Well, since this block is heavier than block B, it will not go up as high after it's released, as shown at the right. Well, that student is missing the point. There's no reason for the block C to go up if it's going to be happy just sitting at this location here. It's displacing the same amount of water in this location as it was in the center of the beaker. So if it heads up, it's going to keep heading up. So that can't be. Student 2, yes, I agree the buoyant force is slightly less than the weight of this block, so it should come to rest a bit below the surface. Well, if the buoyant force is less than the weight of the block, even by a little bit, that's going to give me an acceleration down. The net force causes this acceleration, and so both students are wrong. So student one is wrong because F buoyant would stay constant as long as it's submerged. Submerged with a D, sorry. So it's not going to accelerate at one location submerged and then stop at another location submerged. Student two doesn't understand Newton's second law. F net can't be down if the acceleration is up. Okay, that's the end of the tutorial. I'm going to stop sharing my screen and I'm going to stop recording.